Hi, this is Dr. Viv, and I'm here to talk about complex numbers and Euler's formula. Specifically, I'll be discussing the equation, sometimes called the beauty. Let's take an equation of the form x squared minus 1 equals 0, which you may have solved in earlier classes rather easily by taking the 1 to the other side and taking the square root. If you solve it, you get x equals plus or minus 1. And these are known as the roots or the solutions of this equation. What if you had an equation not with a minus, but with a plus? So I have x squared plus 1 equals 0 instead. This equation is you popularly say it has no solutions because no matter what x value you put, you will always have values bigger than 1. In fact, if you plotted this curve y equals x squared plus 1, the curve that you're going to get would be a parabola like that, which escapes hitting the x-axis because the minimum value it can have is 1. So you would say that it has no real solutions and move on. But as a matter of fact, if you did that, you'd be excluding a big class of solutions given by that. So mathematicians, in an effort to capture that missing class of solutions, introduced the concept of a complex numbers, or in the early days, they used to call it the imaginary number. So they envisaged a process by which you solve this. So you take x squared plus 1 equal to 0 and make it into x squared equal to minus 1. And then you take the square root of both sides. If you did that, you're going to get x equals positive square root of minus 1, and the second solution is negative square root of minus 1. Now, writing the square root of minus 1 is not always fun. So this is sometimes called the imaginary unit, I. So the solutions are either plus I or minus I, where I is the square root of minus 1. How do you picture this though? You'll have to consider a new dimension known as the imaginary axis or the complex axis. So the little industry of visualizing this became very important, and so two people, Gauss and Argand, are credited with coming up with a picture approach. On the y-axis, the traditional y-axis is now called the imaginary axis, and the traditional x-axis is called the real axis. So on the imaginary axis, you'll be plotting numbers like I, minus I, in other words, all multiples of I. I'm just writing multiples that are integer multiples because it looks nice, but it can be any real number times I on the y-axis. On the x-axis, you have the usual positive and negative real numbers, such as 0, minus 1, root 2, pi, and so on. So this is called the Gauss-Argand diagram, or simply the complex plane, and it's indicated by the symbol C with a slash through it. Now, any complex number can be represented in this complex plane. Let's try to represent these solutions. Plus and minus 1, well, that would be these two. And plus and minus I would be those. So you see they lie in a nice little circle of radius 1, and that's a nice way to visualize the solution set. Now if you think about the equation for which these two are pairs of solution, that equation would be x to the power 4 minus 1 equals 0, because x to the power 4 minus 1 can be written as x squared minus 1 times x squared plus 1 equal to 0, and each one in turn will give you those roots. So in a sense, you have found the fourth roots of unity. So this picture is set to represent the fourth roots of unity. Meaning, if I took x to the power 4 minus 1 directly and worked with it, then I would get x to the power 4 equals 1. And if I took the fourth root of this, I'm going to get x equals 1 to the power 1/4. And that has the following solution set. It's 1, minus 1, I, and minus I. So you've really expanded your solution repertoire from just being plus and minus 1 now to 4 distinct things. So these complex numbers were really a big advance in mathematics and led to a lot of important discoveries in several fields of algebra and analysis. Now, if you have any complex number, it's indicated by the symbol z. Z is what a complex number is usually written as. And the x-intercept of z is called its real part, and the y-intercept of z is called its imaginary part. So here's a taxonomy of a complex number. I write z equals a plus ib, where a is called the real part and b is called the imaginary part. You leave the I out of it and just refer to the B as the imaginary part. Now there's a very nice interpretation for this from a physics perspective. You can think of these as unit vectors. So what I will do is this. I'll write this as A times the unit vector in the direction of A, which is the real axis, and the unit vector there is just a number 1, plus B times the unit vector in the direction of the imaginary axis. And there the unit vector is the complex unit I, which is the square root of minus 1. So that's a nice interpretation. It tells you correctly that to get to the point z, you first go A units along the real axis and then go B units along the imaginary axis, and then you arrive at the number that you've called z. So that's the vector interpretation of that number. Now there's another quantity which is pretty important, known as the conjugate complex number. And you should think of it as the reflection of the complex number about the real axis. That is indicated by the symbol z bar, and that's sometimes called the complex conjugate. Z bar is simply the inversion of z, which means that the real part remains the same, but the imaginary part gets inverted. So that's a minus ib. So these are some basics of complex numbers. How do you add, multiply, etc. complex numbers? So adding and subtracting complex numbers is best done in this approach. This approach is sometimes called the Cartesian approach because this is like the Cartesian coordinate system. You take the unit vector in the I direction and the unit vector in the j direction and you add them up. So if you have two vectors or two complex numbers, z1 plus or minus z2, I will indicate both addition and subtraction in the same line. So I'll get z1 is a1 plus ib1, let's say, and z2 is a2 plus ib2, where a1, b1, a2, and b2 are all real numbers. Well, that's just going to be the real parts added together or subtracted, plus I times b1 plus or minus b2. And that's your new complex number. If you try to plot this in your Argand diagram, what would you see? For the sake of convenience, I'll take everything to be in the positive direction. So z1 would be some complex number like this, with an a1 and a b1 there. And z2, you're adding it, so z2 would be another complex number with the projection on the real axis a2, But since this is already A1, that's going to be A1 plus A2. And the projection on the imaginary axis, well, that vector alone is going to be B2, but since it's above B1, it's going to be B1 plus B2. And in this way, we have arrived at the interpretation for the new vector, which is the vector sum of Z1 and Z2. It's a traditional meaning of vector addition in physics. You would simply add the vectors by taking the resultant vector to start from the tail of the first vector, which is Z1, and go all the way to the head of the second vector, which is Z2. Subtraction occurs the same way, except that instead of the major diagonal of the parallelogram formed by Z1 and Z2, you will now be looking at the minor diagonal of that parallelogram. Multiplication and division are not really suited to be examined in the Cartesian coordinate system, and we have to go to the polar coordinate system for that. And here's where things get interesting. The polar coordinate system can be explored in the following way. I'll start by writing my complex plane, and again stick to the first quadrant to keep things just under control. I have a complex number z, and in the Cartesian representation it would have x component A and the y component B, or the real component A and the imaginary component B, if you want to use complex terminology. And just to make sure that you get used to this notation, I'm going to start putting C over here. Now, the polar representation starts by asking, what is this distance out? Well, that distance in polar coordinates is usually called by the symbol r, and the angle theta is measured counterclockwise from the real axis, as is usual in polar coordinates. So r is sometimes called the argument, the modulus, of the complex number, and theta is called the argument of z. These are words left over from the early development of complex numbers. You may or may not want to use them, but textbooks usually have these symbols sometimes. Arg z for the argument and mod z for the modulus. So now you have a new way of representing a complex number, and this representation of a complex number is usually called a phasor in engineering and in physics, and that is, you represent z as a combination of r and the argument theta. Now, electrical engineers like to write it like that. Euler came up with a way to represent this, and I'll tell you about it in a moment, known as Euler's formula. But in terms of basic trigonometry, what can we get from here? We know that A has to be r cosine theta. So it's r cosine theta times the unit vector 1, which I won't write, plus I times r sine theta. That's the y component. So I can take the r outside, and I end up with cosine theta plus I sine theta. Well, the great mathematician Euler showed that this is equal to r times e to the I theta, where e is the usual exponential function. So if you remember from basic calculus, e to the x is equal to 1 plus x squared over 2 factorial, and so on. The most general term would be x to the n over n factorial, and it keeps going, it never stops. Now if you take x and replace it by I times theta, then you're going to get an interesting result. You'll find a set of terms, and this is one of the homework problems. You find a set of terms that assemble the real terms, which assemble into cosine theta, and the imaginary terms which assemble into sine theta. So you can prove Euler's formula simply by writing out the full expansion of this thing. So that is the great formula of Euler. Let's see why this equation is highly revered by both physicists and mathematicians. Now, first of all, before I get into that, I want to show you how to multiply and divide. Multiplication and division, as I promised, is best done using the polar representation or the phasor representation. And you can see that here. If I take z1 times z2, I'm just going to get r1, r2 times e to the I theta 1 times e to the I theta 2. Well, the product of two exponentials is just the sum of those exponentials. So that's r1, r2, e to the I, theta 1 plus theta 2. So the product is just the product of the moduli, and the argument of the new complex number is just a sum of the arguments. And if you take if you divide, you'll get a minus sign instead of a plus sign. So I will not write that. So this is the beauty of using the polar coordinate representation. Now the equation known as the beauty comes when you set theta equals pi. So let's see what happens when you do that. So I'll get e to the I pi equals, well, r is just 1, so that's going to be cosine pi plus I sine pi. Well, pi is 180 degrees, so sine disappears, and I end up getting e to the I pi. The cosine pi is negative 1, which I'll bring to this side, left side, plus 1 equal to 0. This equation is popularly referred to by many mathematics writers as the beauty because it combines very unlikely things: the square root of minus 1, the ratio of circumference to diameter of a circle, the exponential function, the number 1 and the number 0 in one beautiful equation. The physicist Richard Feynman, when he was 15 years old or so, kept a notebook of all the beautiful equations, and to the end of his life he believed that this was the most beautiful equation in all of mathematics.